Okay, so hi everyone, I'm Luigi Tresca, and I'm a second year PhD student at Politecnico di Torino. And in this last session of this tutorial, I'm going to talk a little about how to benchmark autonomous mobility on demand system control policies. Here I just reported the main agenda that will be covered during this last session of this tutorial. So I will start talking a little bit about which are the traffic simulators that you can find in the literature, followed then by the introduction of the available calibrated city scenarios that we are gonna add into our code base, followed by the introduction of the benchmarking control policies available in our repository. Then I will present some results of the three-step framework graph reinforcement learning based architecture that was previously described in this tutorial using a soft actor critic agent on a mesoscopic scenario. Then I will cover how to answer to some design decision questions. And lastly, I will talk a little bit about the generalization capability of the same reinforcement learning-based policy. So since the concept of autonomous mobility on demand system has been deeply investigated during the previous sessions, I would like to start this talk by talking a little bit about which are the different kinds of traffic simulators that are available in the literature. Mainly, it is possible to group these simulators into three categories. So going from the macroscopic simulators to the microscopic simulator and to the mesoscopic simulator. And as you can see here from the plot reported in the slide, sorry, there is an increment in terms of fidelity comes with an high cost in terms of computational requirement, going from the simplest setting, which is the macroscopic one, to the most detailed one, which is represented by the microscopic simulators. So if we look a little bit deeper in the features of this kind of simulator, starting from the simplest one, with the macroscopic setting, these kind of simulators are characterized by an aggregated description of the vehicles inside the network that are aggregated into flows between nodes that compose the network of the graph that describe the city. And in this setting, it is not possible to individually describe the vehicles, allowing so for a fast simulation, but coupled with the lack of reliability of these kind of simulators. On the other hand, with microscopic simulators, it is possible to properly describe the vehicle movement inside the network by introducing some longitudinal and lateral dynamics model of the vehicle. It is possible also to model the interactions between vehicles using some count-following models. It is possible to model the interactions between vehicle infrastructure, such as intersections of traffic light, and other kind of vehicle behavior modeling that you can see listed in this slide, such as the overtaking behavior and some lane changing model. However, this high fidelity comes with an high computational effort. In between the macroscopic and microscopic simulator, we can find also the mesoscopic simulators, which are mainly characterized by the exploitation of the acuity approach to model the movement of the vehicles inside the city. And through this QT approach, the roads or the edge of the network are split into segments that are called Q, that are characterized by having a fixed vehicle speed inside each segment. And this vehicle speed depends on the congestion level of the segment. And with this approach, it is possible to have a more granular simulator, so increasing the computational speed without losing in terms of accuracy in the description of the traffic evolution. In our code base, we implemented all the three simulators, and we used a microscopic traffic simulator, which is called Sumo, which is available on an open source to develop the traffic simulators in the mesoscopic and microscopic setting. Now let's focus a little bit on what is provided within our code base, because we decided to add some already calibrated scenarios of different cities both for the macroscopic setting and for the mesoscopic setting. For the macroscopic setting, some already calibrated scenarios of the city of Chicago, New York, Porto, Rome, San Francisco, Shenzhen, and Washington are available and ready to be used to test some new control strategies, for example. However, in this session, I want to focus a little bit more on the features of the Sumo-based traffic simulator, presenting also some results of different benchmark control policies on this kind of simulator, and more in particular in the mesoscopic setting. Also in the mesoscopic setting, there is an already calibrated traffic scenario, which is based on the city of Luxembourg. And in this scenario, it is possible to operate in a detailed description of the city that is coupled with a 24 hours traffic scenario that for sure is developed in Sumo, and it was previously calibrated in the work that you can find referenced in this slide. The city is characterized by a network with around 2,000 nodes, with the traffic demand that is described with a 24 hours data set of vehicle trips. However, with the autonomous mobility on demand system, we need a description of the passengers' drive demand. So a question that could naturally rise is how to generate this demand starting from the vehicle trips dataset file that is usually available with all the different kind of city and scenarios calibrated in Sumo. So in order to answer this question, first of all, we need to provide the simulator with a cursor description of the network. And so we need to spatially aggregate the original network in a smaller description of the city. First of all, because we could need to aggregate the information, spatial information of the demand. And second, we need to also reduce the dimension of the network if you want to use a graph-based control policy, mainly because of computational effort reason, such as, for example, some reinforcement learning tool or model predictive control tools. Then once that we have clustered the original network into regions, a methodology that can be followed for generating the passenger demand consists in the division of the trips dataset into mainly two categories. So the first one is characterized by some exogenous traffic, which are vehicles that cannot be controlled by our AMOD control system, while the second one is the effective passenger drive demand. That is the one that will be post-processed in order to achieve something that could be input in Sumo in terms of passenger travel demand. And this split is performed using a fixed probability that in this case is about 15%. So once that we've done this division of the initial trips dataset, the passenger travel demand trips are post-processed using a clustering algorithm in order to identify the origin and the destination regions. And after that, the clustered trips are used to fit some time-dependent Poisson distributions for each origin-destination pair, with the goal of using a statistical model to sample the demand and generate the origin-destination passenger right request that is then passed as input to the Sumo simulations. Lastly, there are also some available policies that can be used as benchmarks for testing different policies or for calibrating new and different scenarios that can be added to the repository, and which are listed here in this slide. So first of all, we have an optimization-based policy, which is an MPC policy that is provided with two different flavors. So there is an MPC policy that has the perfect knowledge in advance and complete knowledge in advance of the travel demand. And the idea of these control policies is to provide an upper bound in terms of performance. The second MPC controller has embedded not the complete demand of the complete demand, but a prediction model that will forecast the demand during the time horizon of the simulation. Then also two heuristics are available. So the first one is an equal distribution policy, which is a policy that mainly tends to equally distribute the taxis in the city. And the second one is a policy that is called Plus One, which is a policy that mainly tends to rebalance the taxi to each region each time a taxi is matched to a passenger starting from the same region. So basically, this policy tends to move a vehicle to a certain region each time a vehicle leaves that region, for not for rebalancing purpose, but for serving one passenger. So if you're interested, of course, in using our code base, you are free to give your contribution by adding new control policies and new sumo calibrated scenarios. Okay, so once that a new policy has been introduced, it is also possible to use this simulator to extract some evaluation metrics that can span between pure economic evaluation metrics to some metrics that evaluate the transportation network performance. For example, if we are talking about economic evaluation, we can evaluate how profitable is the policy, how effective is the policy in serving the passenger demand, and how effective is the policy in minimizing the rebalancing cost. While if we're talking about transportation network performance, we can evaluate how efficient the fleet is used. So if it's able to minimize the idling vehicles, which is the average waiting time per region, and which is the network congestion level due to the policy strategy, the balancing strategy. So after a quick presentation of the main features of our AMOD system simulator, in the next couple of minutes, I will show you some results of the soft actor critic based policy integrated into the trip-step control framework that was previously introduced in this tutorial. And the performance of this methodology will be compared against the benchmarks that were previously introduced in this presentation. So the performance will be assessed on the mesoscopic simulator in the city of Luxembourg and in a scenario that takes place during the night, with the main purpose of performing a pure profit optimization task, as you can see here reported from the reward function, which is reported in the middle of the slide, which is characterized by two main terms. So the first one is the price, so how much we can collect by serving one passenger, while the second term is a term proportional to the cost of rebalancing the vehicle or the cost associated to the movement of the vehicle inside the city. So the performance of the agent was tested in 3 different demand settings, which can be selected in the code that we're going to share. So the first one is a station-based setting in which the demand can appear only in the center of a region and can be directed again only in the center of the destination region. And the same concept is valid also for the balancing, because vehicles can move just between centers. While the second scenario is a random origin destination setting in which people can appear in the network on a random node inside the origin region, and the same is valid also for the destination region, and same concept can be also extended for the balancing. While the third scenario is again a random origin destination scenario, but in this case, a maximum waiting time for passenger is added that for these results was selected of 20 minutes. And if a passenger waits a time that is higher than this maximum waiting time, will be removed from the simulation, and for sure it will not be available to be served by the MOD control system. And I decided to present this in terms of bar plot for the three scenarios, and evaluating the performance in terms of profit, served demand, and rebalancing cost. So if we look at the profit, we can see that the proposed soft actor critic policy is able to outperform both heuristics, so the equal distribution and the +1 policy, while being able to achieve profit performance in line with the upper bound in terms of performance that is provided by MPC with the complete knowledge of the demand in advance. However, if we look also to the server demand, we can notice that in this case, our methodology is the one that serves less demand if compared to the other control strategies, even if the demand is quite close to the other three control strategies. While it is also able to achieve the minimum rebalancing cost with respect to benchmarks policy. And this behavior can be mainly explained since we are not looking also at the server demand in terms of optimization, but we want to perform optimization that just look at the profit. So in addition to the economic analysis of the policy, we can also inspect more in detail how the policy behaves. In fact, in the bar plot reported on the right side of the slides, there are two bars. So the red one is a bar that is proportional to the demand that will globally appear during all the episode in each region, while the other bar is represents the incoming vehicles in each region, split into two different incoming flows. The blue sky one represents the vehicles that will arrive in the region due to matching purpose, while the blue one represents the vehicle that will arrive in the region for a balancing purpose. And globally speaking, ideally, the two bars should be as close as possible. As you can see, for example, that the agents is able to do for region 7 and region 9, since the goal of the rebalancing strategy is trying to close the gap between passenger trip demand and incoming taxis from previous trips for each region. However, this global behavior is not always present, as you can, for example, see happens in the region 5, 6, and 8. And if we look at the behavior of the policy on a more local visualization and time-based visualization, we can see that this behavior leads to an accumulation of waiting passengers in this region. As you can find out from the plot that is reported on the right side of the slide, in which a temporal analysis of the unserved passengers demand dynamic is reported. However, after the first accumulation phase, you can see that the policy is also able to serve the accumulated demand. So lastly, another additional analysis that it is possible to perform with our simulator regards the inspection, for example, of the average waiting time per region, as you can see reported in the plot on the left side of the slide, and which is the fleet utilization performance as reported in the plot on the right side of the slide, in which three different ratios are reported between vehicles that are moving inside the network, vehicles that are idling inside the network, and vehicles that are in rebalancing mode inside the network compared to the fleet dimension. And I want to point out that the scope of this session is not only to show the results of the proposed methodology, but also to show which kind of analysis it is possible to perform with our simulation. So spanning from economic analysis to global performance analysis to more local and time-dependent performance analysis. So after the presentation of these results, now let's try to understand how to use this simulator to answer to some questions that can arise during the AMOD system calibration phase. That, for example, can be represented by some questions regarding which is the appropriate taxi fleet size, how to calibrate the impact of the cost to the total profit, because this parameter could be important because since we are performing an optimization task that aims at optimizing the profit, the impact of the cost will directly impact also the behavior of the policy. And lastly, also we can solve some questions regarding which is the appropriate number of region to spatially agree the initial network of the city in order to achieve cursor description of the scheme. So starting from the fleet dimension calibration, an approach that can be used consists on the exploitation of the optimal solution coming from the model predictive control with the complete knowledge of the demand in advance, and collecting data also with a heuristic policy that, for example, can be the equal distribution. So we can use the trend of the MPC policy as reported in the plot on the left side of the slide, in which the served demand and the profit for both the policies are recorded. We can use the trend of the MPC in order to evaluate how the served demand and how the profit changes with different fleets in terms of dimension. And the idea is trying to find a compromise between a policy that it is able to be profitable for sure, and able to achieving a nice demand satisfaction. However, what we want here is a policy that is able to serve the majority of demand, but not having too much idling vehicles, because in that case it will be over-dimensioned. And we can also see at this comparison, at this last point, by comparing the performance of the MPC in terms of profit with the performance of the equal distribution. Because there should be a gap for sure between these two policies, because the heuristics tends to overperform if applied to sites with a higher number of taxis available, mainly because the heuristics rebalancing strategy is not optimized, but it's mainly based on rule, and so they tend to overperform with overdimensioned fleet. Another additional aspect that could be taken into account regards the effectiveness of the policy in serving the passengers, that can be evaluated, for example, by look at the plot reported on the right side of the slide, and in particular the blue line, which represents the average waiting time of passengers inside the network. Because with an underdimensioned fleet size, we will see that the waiting time of passenger will explode. And of course, we can also look at the utilization efficiency of the fleet for the reason that I previously explained, because with the higher over-dimensioned policy, we can find that the utilization factor will be too low. And it means that even if the fleet perform well in terms of profit and served demand, there will be too much idling vehicle that for sure is a situation in which we don't have a great efficiency of the exploitation of the transportation system. So passing to the second question, another important factor that influences the policy behavior and the performance metrics is how to calibrate the impact of the cost on the total profit of a model system. This is important, as I already said, mainly because there is a calibration factor, which is this beta factor here reported on the slide, that is proportional to the cost, and that impact also the behavior of the policy, since we want to maximize this reward function that is the profit in this case. So one approach could be using again the MPC with the complete knowledge of the demand to collect data with in a fixed scenario with the fixed fleet size, and switching between different cost calibration parameters. The idea also here is to compare the performance of the MPC with the performance of a policy that will not rebalance any vehicle. Because if you are using a cost that is too high, we will see that the performance of these two policies will be quite similar, mainly because the MPC will tend to do not rebalance any vehicle or rebalance very few vehicles during the simulation. And so also in this case, there should be a gap between the performance of these two control policies. And once that a reasonable parameter have been found, you can also try to find online if there are some publicly available data set, and compare the resulting cost with the cost that is available in the data set. So last question that will be analyzed regards the decision on how many regions should be used to spatially aggregate initial network. And for sure, there is a clear trade-off between the accuracy of the information provided to the policy and the computational time that is required to perform one decision step, as you can see here reported from this two. So if we look at the performance, in this plot, I reported the percentage deviation in terms of profit of the SAC and the heuristics policy from the MPC1. And I reported the trend with different number of regions. And as you can see here, the heuristics tends to increase their profit with a higher number of regions, since a more detailed description of the network allows to better distribute the vehicle in the city. While the reinforcement learning, the agents training tends to be more complex with higher number of regions, mainly because there is an higher action space that should be investigated by the agent. And so, for example, so far we were not able to achieve very good performance with scenarios with more than 14 regions, as you can see here from the drop of the performance. Lastly, in terms of computational power, we can see that there is a difference in terms of computational request between the MPC, the important learning-based strategy, and the heuristics. And you can see here that the MPC presents an exponential trend of the time per decision with a higher number of regions, while the performance of the reinforcement learning-based strategy are in line with the heuristics one. And this allows to theoretically select the final spatial resolution to describe the city for these two policies is compared to the MPC1. So the last section of this session will regard the generalization capability across different number of regions of the graph reinforcement learning-based risk control policy. In fact, in this plot, again, the percentage deviation from the MPC performance in terms of profit of an agent trained on scenarios with different regions, which is here represented by the yellow line, we compared against the generalization capability of a scenario trained on 10 regions and then tested on a scenario with different regions. And as I highlighted before in the previous section of this presentation, we can see that it's harder to train agent on environment with more number of regions because of the action space. And so we can see here that there is a drop in terms of performance, while the agent tested on the 10 regions scenario is able to well generalize in terms of profit on all the scenarios considered. So if we do a deeper analysis of the behavior of the agent, highlights that the performance drop of the ACC agent trained with different regions increased because of an increment in terms of rebalancing cost, while it's able to properly serve the demand. While for the generalization capability of the agent, we can see that the profit trend is mainly due to mixed results in terms of server demand that tends to decrease with higher number of regions, but that is coupled with also some rebalancing cost that sees and presents decreasing trend with the higher number of regions. And these two aspects tends to compensate and maintaining the good performance in terms of profit. So to conclude this presentation, we presented an MOD system simulator that presents three different actually simulators that has different level of fidelities. So starting from the macroscopic one and going through the mesoscopic and microscopic ones. And in these simulators, there are also some already calibrated scenarios of different cities. So the idea is to use the simulator as a test platform for innovative autonomous mobility and demand control strategies by both training and testing reinforcement learning agents, for example. And we also provided some available benchmark policies, which are MPC equal distribution and +1 that can be used to benchmark the performance of new control policies. And we also showed that we can use also this simulator to answer to some design decision questions that can be, for example, how to mention the fleet, how to calibrate the cost, and in how many regions to spatially aggregate the initial network of the city. So that's it for this speech, and I want to thank you all for the attention. And of course, reach out to us if you are interested in contributing in the development of this repository. And here you can find a QR code that will link you directly to the GitHub repo that we are going to share with you. Thank you.